Hello, my name is Eber Barbero, and today I like to talk about reticulated structures. This is a lecture for MA 343 Intermediate Mechanics. We are in Chapter 3, reviewing statics. All right, so what I would like to do today is talk about reticulated structures. Reticulated structures, as the one you can see in this picture, are extremely efficient, and therefore they are common in practice. So they are very peculiar in that all the members transmit the loads in tension or compression. There is no bending, and that's what makes them efficient. We will discuss this in detail when we get to beams, and I make a comparison between beams and columns, or beams and struts, and we will discover why this happens. For now, we just say that it happens. The New River Gorge Bridge, and it's one of my favorite places to go. You can see because of the beauty of the landscape and the impressive achievement of engineering. This is a 3,000 plus feet long bridge. It carries 4 lanes of traffic, highway traffic. And to accomplish that in a single span bridge, the structure has to be very light. And this is accomplished with an arch, which is here. And the arch is built as a reticulated structure as well as the substructure for the deck. And then I took a little piece here and I blow it up here so you can see how this structure is constructed, all right? And this is the reticulated structure. Now later on I'm going to tell you that all reticulated structures are joined by pins. And then you can go back to this picture and say he's lying because there are no pins here. However, these connectors are so flimsy, so light, that really they do not transmit bending loads. As a result, all these members are subject to tension and compression. The arch, of course, is subject to compression, and that's how this structure is so efficient. Of course, we're not going to analyze this bridge. This is a civil structure, and in this class we emphasize machine design and aircraft structures. But anyway, reticulated structures are the same in any field. And so we will try to review a little bit how to analyze simple cases so that you can do homework and you can work in machine design as well next semester. All right, so then we're not going to do the bridge. We're going to do a simple 2-bar structure. And so which is this? There is this bar, vertical bar, which is pinned here to the support, and then there is this other bar here at an angle, and that is pinned here at the support. And it has to be an angle, because otherwise you could not hold this load P horizontal. Now in this example, we're going to go a little bit further than just calculating reactions and internal forces like we have done until now. And we're going to calculate the displacement of point B. Point B is this point. In the direction of the load, all right? So in this direction, we're going to calculate that displacement. Okay, so to calculate that displacement, we're going to have to calculate the forces in the members so that we can apply the well-known formula for the elongation of this member and the elongation of this member. And having the elongation of this member will allow us to calculate the displacement of point B in this direction. So we need this internal force, and to get the internal force, we have no choice but to first calculate these reactions. All right, so I also illustrate this to show you how important it is that you know statics and mechanics of material basic concepts, because all the problems start like this. So if you cannot do the basics, then you cannot go to advanced topics, all right? You cannot go to fatigue design, chapter 6 in this class, because all the problems require that you do the statics and then you calculate internal forces, do bending moment diagrams, and know how to work with Morse circle. So the foundation has to be there, and that's why we're reviewing everything, okay? So this is our problem statement. Calculate the displacement of point B in the direction of the load P, okay? Now here I introduce another idea, okay, concept, which is always we have an actual representation of reality, more or less looks like the real structure. And then we have what we call a model, which is a more engineering mathematical representation, which is more tractable from a mathematical point of view, and we can analyze and we can design. So always we'll do this, we'll idealize the structure into a model, all right? For example, one of the things that we have done here is that each of these bars now is represented by a line, and this line is the location of the neutral axis or the centroid of the cross section, all right? And of course, this goes through the pins there. Okay, so you see for us, the structure becomes two lines. All right, now when we go from this structure that has a 3D geometry, because they have width and also there is a thickness to these bars, so that means they have area and they have second moment of area as well, I. All right, and then all this information is not lost. We have these lines, but then we have, okay, this line will have area and we'll have second moment of area. So all the information that we sort of lost or we think we lost when we move from a real, let's say, picture, more or less real picture of the reality to just a line, and that information is not lost because we know the area, cross-sectional area, and we know the second moment of area. And with that, we can calculate things with the model in a very efficient way. All right, and it is my job to show you how to do these things. Okay, so next, some facts about reticulate structures. First, in a reticulated structure, all members are joined by pins, okay, or almost pins, like in the case of the bridge. Now, since the pins cannot transfer moment, all members are bending free, moment equal to 0. And actually, that's what makes the structure efficient. All right, we'll discuss this further later. Okay, so bending moment in any of these members is 0. All right, because there is no way to transfer bending moment inside any of these bars. Furthermore, these members can only hold axial load in tension and compression. So in any of these members, this one or here, the load has to go in this direction. There is no other way the load can go. It has to go from one pin to the other pin. All right, and so here go this direction. All right. Now, since member OB is vertical and the load has to go in this direction because this is a reticulated structure, so the load, the only way it has to go is this way, then all the force in OB, internal force in OB, equals the reaction R sub 0, all right? So OB is in compression. If R0 is positive, when we do the analysis, if R0 comes out to be positive, you know, I put the arrow in some sort of arbitrary orientation that I pick. And if it comes out to be positive, then the member is going to be in compression, all right? But since the force, this force equals exactly R sub 0, you see there is no R sub x. I didn't even bother drawing R sub x here because I know that if the member it's vertical, then all the internal force will be equal to this reaction, and there is no reaction here. This Rx that I didn't draw is equal to 0. So these are some of the things that are important to know about reticulated structures. So if you know this, you already know that you don't have to calculate this, so you don't have to waste time doing summation of moments or something that we could do to demonstrate that this is 0. No need. We know it's 0. Now over here, no, because this is at an angle, so a force at an angle in this member, it will have to have two components, one Rx and one Ry. Maybe the directions are wrong, the arrows that I pick, but it has to have two components, right? It has to decompose into two. But here it doesn't decompose because the reaction and the member are aligned. Okay, so now we start working on the problem. The load P is 800 newtons and the angle theta is 60 degrees. So these are the data for the problem, all right? Also, we know that H, this height is 900 millimeters. And with that information, I calculated for you the distance D, which is handy to have, at 519.6, okay? So now we want to go for the reactions first. Okay, one reaction we know is 0, so we don't worry about that. And then we say, okay, first summation of forces in the x direction is equal to 0. So the only forces in the x direction are Rx and P. And since I was lucky, I drew this pointing this way and P is pointing this way, then Rx has to be equal to P. Because there is nothing else, here there is no X, and there is nothing else that is going to hold this P. So this P is held by this Rx, and it's 100 newtons, okay? Now, of course, after you have this Rx, things happen. So next, what we have to do is we have to try to calculate this R sub y, which is part of the technique about solving reticulated structures. We want to try to resolve everything at a node. This is a node. The end of a member is a node. So at this node, we already know Rx, so we say, oh, why don't we just try to get R sub y? So how do we do that? Summation of moment with respect to O. Okay, why respect to O? Because I don't want to deal with this R0 that right now I don't know how much it is. You see, so I eliminate it. So I take moment with respect to O. So moment with respect to O. Then okay, I do P multiplied by H. Yes, counterclockwise. And then what else? This Rx. Well, this Rx will produce no moment here because the distance is 0. And so perpendicular distance is 0. And then I got Ry multiplied by d, which is also counterclockwise, so it's also positive. So it's pH plus Rd equal to 0. Therefore, Ry is this, negative 1385. Okay? So that means that this arrow should have been going down. Well, no problem. We see the minus sign there. We understand everything. Okay? Okay, so then next we have one more equation that we can use. That is summation of forces in the y direction. Yes. And so if we look at here, there is nothing in the y direction, and the only things that are in the y direction are these. And this says that R sub 0 plus R sub y has to be equal to 0, because that summation of force equal to 0. Therefore, R sub 0 is minus R sub y. And since R sub y is negative, this will be positive. And we have to remember these numbers because we need this to move forward. Okay? All right, so next, now we go into the internal forces, all right? And we want these internal forces with sign. If the sign is positive, that means it's traction, all right? So we start with member OB, which is the easiest. OB is the vertical. And since R sub 0 is 1385, we push on OB, then obviously OB is in compression. Therefore, FOB, the force, internal force FOB is minus 1385 in compression, because R sub 0 is positive, so it's pushing on this member, yes? And okay, and so then we go to a member AB, and all right, the force in member AB will be the resultant of Rx and R sub y. R sub y is negative, so the arrow actually should be pointing this way. So we do this arrow square plus this arrow square root to get the resultant. And the resultant is here, and it's 1600 Newton positive tensile, yes? And if you think about it, yes, it makes sense. When you put this load P, this bar becomes tension, and then this bar goes into compression, and then everything is in equilibrium. You can think about it, okay? So, all right, so now we have the reaction, and we have the internal forces. The internal forces is FOB minus 1385 in compression. FOB is the internal force in this member, and FAB in AB, which is this member, is 1600 in tension, okay? Now, to calculate the deformation at point B, first we have to calculate the deformation in all the members. And to calculate the deformation, we'll use this well-known formula. The elongation of a member delta is force times length divided by modulo elasticity times area. And so the modulo elasticity of steel is 207 10 to the 3 megapascals. And the cross-sectional area is 81 mm square. Okay, so another thing that you may want to get used to is that I don't like to work in pascals and meter squares because those are crazy values. Megapascals go with millimeter square and newtons very nicely. Okay, pretty much the way KPSI go with inches in the US system. All right, so we need to use delta FL over EA, and for that I'm giving you the modulus and the cross-sectional area of the bar. All right, so then we calculate the elongation of each force, of each member, because we know the internal force. And so member OB, which is the vertical, FOB is minus 1385 that we calculated before. So we apply the formula, force minus 1385, length is 900, remember H is 900. Divided 207 10 to the 3 times 81, and this is going to come out this way directly in millimeters. Okay, so then we go to member AB. FAB from our calculation before was 1600 newtons, which was the resultant of these two arrows with this arrow flipped. because the number Ry came out negative. And so then we need the length of the member AB to put in the formula here. And that is easy because d squared plus h squared square root to give us the length of the member. So we do 1639 divided by this, and we got this delta AB. So this is how much delta OB is how much this bar shrinks, and delta AB is how much this bar stretches this way. So once we have that, then now we do drawing of the formation only. That will be a fancy term for that is kinematics. So, okay, so we say, all right, at this point, delta OA is this and is negative because remember it was in compression, but it doesn't do anything to help us with the delta B, which is this displacement. Remember, we need the horizontal displacement of point B, which is going to be this way, but I drew it up here. I like it better to draw it up there. It's the same. So this delta B is this displacement, and the way I can calculate this displacement is I can take the delta AB, which is the stretching of this bar, all right, and then multiply by the sine of this angle, which is the same as this angle, so that's alpha. All right, that's what I'm going to do. So delta B is delta AB, which I already know what it is, multiply sine of alpha, and the sine of alpha, how much it is d divided by this, so d divided by this is sine of alpha directly, that's 0.5. So I get to this final answer. So I know the displacement in the directional load, which I can use for whatever, okay? So then I guess we have some conclusions for reticulated structures. Remember, all members are in tension or compression only. That means that the force goes along the member and they cannot carry any moment. To calculate the reaction, you calculate the reaction as usual because the structure as a whole, then the structure, yes, it can carry moment. So you can do summation of moment equal to 0 on the whole structure to find out stuff like we did. So you go back and you review, you'll understand. However, this is a very simple example where calculating the reaction solves everything. If the reticulated structure has several members, then one has to find a strategy to solve one node at a time and advance until you get the answers on all nodes. And whether we do this or not depends on what examples we need to do later on in the class. For now, I think that knowing how to do simple reticulate structures, it will help you a lot, particularly for machine design, okay, where there are simple reticulated structures, usually not very complicated. For aircraft structures and civil structures, the reticulate structures could be very complicated, but they are always easy to solve. It's really not a problem. As usual, we have homework on web work at that address over here. Next lecture will be internal forces in beams, and we're getting close to diagrams, which comes after that. Okay, so with that, I thank you very much for your attention, and I'll see you soon.